So I'm working for CloudFlare, and we have an office in Singapore, and we are hiring, of course. I was told I need to say that. That's the first thing. I'm an engineer, and I work on the DDoS defenses. So I'm responsible for keeping CloudFlare online during all those attacks. Unfortunately, I'm not going to speak much about that today. I decided instead of speaking what I do usually, which is to speak about packets, gigabits per second, peering links, internet transit providers, and how fast are our network cards. I'll speak about something much more geared to this audience, which is about how we use Go for that. So let's get started. So yes, we are CloudFlare. What we do is we provide a proxy services. If you haven't heard about us, how it works is basically you change your DNS names on your website to our services, and then we will proxy all the traffic through our servers. And the advantage of this model is that all the HTTP and DNS traffic will go through our servers, and we can then stop traffic which we think is invalid, which we think is evil or threat to your services. This is fairly interesting. This really does allow us to actually be in front of your websites and basically shield from all the malicious traffic. We do have a pretty large network. I actually lost count, but about 70-something data centers around the world, and this number is always increasing. So we really have servers everywhere, and not only we provide the denial of services, but we also speed up websites because we cache stuff. So you can think about that as a kind of fancy CDN with a bit of DDoS, or the other way around, or as fancy DDoS with a bit of CDN. We are content neutral. We really have plenty of customers behind us. I think 2 million was the last public count of 2 million websites that are behind us. We have everyone. We have from dating portals through social networks to government agencies. The funny thing is that different government agencies from different countries are using our services. So we are content neutral, we really are. And this causes a problem. This causes a problem because many people don't like some of the content in the internet. Some Palestinians, for some reason, don't like Israeli content. Some Israeli people don't like Palestinian content. And this is a problem because those websites are being attacked by different forces. Is that anonymous? Is that something different? Depends. But we are then shielding those websites from the denial of service attacks. This is a chart of denial of service events per day, or attempts per day, over I think 3 months. So the general trend is that we see something between 20 or 30 and 100 denial of service events on every day. And on some days it's much higher, it's more like 400. If you go to our blog.cloudflare.com, then you can read a recent blog post in which we describe February attacks. We had a fairly busy February in which this counter jumped to 1,400 or 1,200, much larger. Anyway, so this is kind of the general trend. So what's the problem? Why that is a problem at all? Welcome. The problem is that, generally speaking, defending from denial of service is harder than launching bigger attacks. So basically, it's easier to scale out the attack than to scale out the defense. This is the general problem with denial of service. So the idea of denial of service, if you don't know, is that you basically overwhelm the attacked resource, website or DNS server or something different. You just overwhelm it with something. It can be something that attempts to overrun the CPU on the end machine, or network, like physically saturate your network card, or it's something different. But the idea is that you overrun the target. And if the target is overrun, it doesn't have enough resources to answer legitimate traffic. So the problem is, it is actually fairly costly to buy more networking gear. If you are on the defender side, you have to pay for the bandwidth, you have to pay for more CPU. So it actually does cost you money, and it's not easy, it's not always possible to buy more capacity. While on the attacker side, it's trivial, you just add one more bot anywhere in the world and you just send more traffic. So this is scaling out the attack is much easier. Generally, hand-wavy speaking, there are two types of attacks. One is what we call layer 3, and the other one is what we call layer 7. So in layer 7s is what you would call kind of normal HTTP requests. If you see TCP connection, and then some requests flowing in, and that's from many bots around the world. That's L7. But I'm much more focused on L3 attacks. L3 is when we see packets coming from somewhere which have spoofed source IP address, basically random or some other, basically malformed, or pretty much fake. And this is a much bigger problem, at least it was a much bigger problem for us. And the reason is that attribution is hard. If you see packets flowing to your network that you don't know where they are flowing from, then you don't know where they are flowing from, which makes defense harder. And the other thing is it's very hard to it's not obvious to distinguish the good packets from the bad packets. So actually to react, how do you know if this traffic is actually illegitimate or legitimate? A good example could be SYN packets. If you have a TCP connection, you know it starts with a SYN packet, how do you know if that's a packet which is forged by someone somewhere, or it's actually a legitimate customer? This is an example of layer 3. Layer 7s are a bit easier, mostly because IP reputation works. If you see big number of connections coming from a single IP address, then this IP address is there because the full handshake was finished. So it's a bit easier to defend. So I'm focusing on L3. My job is to do layer 3 kind of spoofed packets defenses. So this is how the attack could look like. This is the attack actually one of the kind of real charts. This is number of packets per second hitting one of our boxes. If you don't see, the general trend is we receive about 50,000 packets per second on the usual traffic, and then the attack happened, and it peaked at about 800,000 packets per second. So you can see that the volume, the physical volume of packets was actually fairly large. It's actually fairly easy to spot that this attack is happening. So in order to defend from that, we have a full-blown defense system. This is kind of the high-level overview of how it works. We have an attack detection system, which I will focus in this talk on. Then the attack detection system detects the attacks and feeds this attack information into our reactive automation system. The reactive automation is pretty much business logic, so it's kind of much more about what customers, are they enterprise, do they have their own IP addresses, is the attack actually legitimate? We have very often attacks which don't go to our real IP addresses, they go to unused IP addresses. And then we have mitigation database with mitigations, which is pretty much a glorified IP tables, so Linux firewall. So once again, the system basically detects attacks, then it goes through some business logic, and at the end we spit out IP tables. This is kind of high-level overview. So yes, I'll focus on the attack detection part, and why is that? Well, it's because it's in Go, obviously. At CloudFlare we have plenty of infrastructure within Go, and so this is just one of the pieces. The most interesting for me because I'm kind of dealing with that every day, but we have many other pieces in Go as well. I think we were one of the earliest users of Go out of kind of in the corporate world. Anyway, so how the attack detection works. So how it works is we have switches. In each and all of our data centers, we have our own switches. We don't use any cloud infrastructure. We have our own physical hardware. And those switches have a magical feature called sllow. And sllow is a fancy protocol which basically allows switch to send UDP packets in the sllow format with samples of packets that are flowing through switches. So basically you can instruct switch to inspect every nth, like 1,000 or 10,000 packet that's flowing through the switch, and you can instruct it to put it on the sllow payload and ship it to a central IP address, some IP address. So this is what we do, and that's why in our central location, in our central place, we actually receive all those sampled packets and we know what's happening. We will not see all the traffic, it's only sampled packets, but we will definitely notice the big attacks I'm talking about here. We will definitely notice 800,000 packets per second hitting on our servers. So how our system actually algorithmically works. So we are using streaming algorithms, and this is now an exciting moment. Is the rest of the talk going to be exciting or not? So who have heard about streaming algorithms? Does it ring a bell, or is it okay? That's one, two, maybe. Okay, so a couple of people. Okay, so in this talk, if you know about streaming algorithms, you can leave now. In this talk, I'll describe the streaming algorithms we are using. Okay, so what are streaming algorithms? Streaming algorithms is a general concept. This is very much not scientific description of an algorithm that you feed constantly data in. So in normal algorithms, normal data structure that we learn in school is you have all the data, like, I don't know, SQL database, you have all the data present, and then you do some operations on that, some trees or indexes or something. But the point is you have all the data available. It's there, it's sitting in the database, on a disk, on a file, in your Excel spreadsheet. In streaming algorithms, the idea is that you don't have that. You have constant stream of flowing events, of flowing things. And you can think about it, okay, but if I just store last hour worth on disk, then you can just do normal analytics on that. Yes, but the whole idea of streaming algorithms is that A, the stream is infinite. You assume that the incoming data are gigantic, they are just always flowing, and it's not flowing because it's flowing for a reason, and it's flowing because you cannot store that. And the other thing is, it's not bounded. We don't know how many attacks there will be. We don't know how many IP addresses we'll see. In normal world, you can assume you will have at most 1 million users. We have no idea. Like, we really don't. So yeah, so streaming algorithm is much more of a black box that constantly gets data in and spits out some results, and they are usually real time as well. They usually are coming as the algorithms kind of goes. Because it's the flow of data is infinite, that's the kind of assumption, you cannot make definite counting. You cannot have definite answers. So the algorithms are usually approximate, usually trade memory for the accuracy. And yes, obviously the attack detection is streaming. It's streaming for two reasons. One is I want to have the attacks being detected in real time. I don't want to have a system that sits there for 5 minutes, aggregates the data, and says, oh, in the last 5 minutes, I saw these packets, because then they have 5 minutes delay by definition. I don't want that. I want to have real-time events as they are happening. And then the data that are flowing in, the packet samples I described from the switches, this is actually a real stream of real events that are flowing in this kind of infinite stream. Okay. So I will describe 4 algorithms, so hooray. We'll start with exponentially weighted moving average. Does it ring a bell, anyone? That's similar. If it doesn't ring a bell, don't worry, you did hear about that. You are using that on a daily basis. Maybe you don't know the name, but this is a very popular algorithm. Then I'll speak about space saving. Space saving is less known. But space saving is pretty simple and quite awesome, so I hope I'll encourage you all to implement that in your spare time, because it's really one of the very simple streaming algorithms which is very powerful. Then I speak about something very custom to us, which is what I call simplified hierarchical heavy hitters. This is very custom to our use case, but maybe it will inspire you again to experiment, because this is pretty much an application of a well-known algorithm. Again, it should be quite simple. And finally, my favorite, which is hyperloglog. But let's leave that for the last moment. Okay, so what are we trying to achieve? What are the attacks that we want to find out about? What do we actually want to get out of this exercise? So let's start with the simplest thing. So I have all the samples coming to my system. The switches are telling me, okay, I saw packet from here to here with this payload. Okay, let's say I want to do the basic possible, the simplest possible thing. I want to get this data and spit out a report like that, which is an IP address, a destination IP address, my IP address, and how many packets do I see coming into it. Simple, right? I want to see that in real time. So let's define real time in this case as, let's say that the black box will spit out this report every second. So every second I'll see this report on my screen. This is fairly real time enough for our use case. Okay, how to do that? Well, in the naive approach, you will have a table in your memory in which you will have 2 columns, 1 packet per second, the other is IP address, and every new sample comes in, you find the IP address, and you bump the counters, and you move on. Very simple. Unfortunately, it's not that simple in practice. It's because what do we mean by packets per second? There is no such a measurement. It's not an SI value. It's not a unit. So everyone that speaks about packets per second speaks about different things. You need to define exactly what you mean. You can say, okay, packets per second for me is number of packets going to this IP address I've seen over last 1,000 milliseconds. But then what about bursts? You can have 1 second in which you see million packets, and then next second when you see 0 packets. So you want to see 0? Not really. So the naive approach of kind of storing the samples in memory and then kind of counting them won't work. A, because that's not actually the measurement you actually want, and B, you actually need to use memory for that, and you have no idea how much memory that will cost. So that's not a good approach. So what you generally do is you count the kind of differences in each sample that comes in. You count the assuming they are distributed evenly over time, how many PPS that would be. So in this case, it would be like very variable numbers, and you see something like that. You can see bursts, you can see packets coming very often or not very often. So that's again not very useful. So you need to smooth it out. And to smooth it out, you use the exponential weighted moving average algorithm. And I told you before that you actually know that algorithm. You do not know because if you know what Linux load average is, or any Unix load average, this is the algorithm. So once again, who've heard about load average on machines, on servers, on your desktops? Anyone? Anyone? Of course. So how it works under the hood is that's exactly it. So the load average that you see on your machines basically takes every 5 seconds, counts number of processes in your machine that are in runnable state, and then it does this smoothing algorithm over that. So how it works? I'll spare you the math for today, although the math is quite simple actually. But I'll describe in general terms how it works. So this is the free load average that we usually use, which is one average with the decay time of 1 minute, 5 minutes, and 15 minutes. And this is when you charge them with a value of 1. Okay, so basically on time 0, we had one process in runnable state. So this was value 1. And then you can see those three values kind of getting there quite steadily and smoothly going up to that value. And you can see that 1 minute, that the 1 minute average goes, receives, I don't know, the value 0.9 after, I don't know, 90 seconds about. The definition here of this 1 minute is that in 60 seconds, the value will charge at most half. So this 1 minute here means that in 60 seconds, we will have at most 0.5 value here. We are charging it with 1. So in 1 minute, it will charge at most half. In second minute, it will charge from 0.5 to 1, half of that. So that's why the curve is so kind of smooth here. Anyway, so basically you can use different kind of curves. How about the decay, the discharge? The discharge is similar but kind of reversed. So basically the 1 minute average will decay very quickly if you stop charging it, if you put value 0, and the others will discharge a bit smoother. Anyway, the idea is that you can smooth out all those graphs. I told you the math is easy. So what you have to do if you want to play with that? Well, either you can read more about exponentially weighted moving average. By the way, in the literature there are main names for that particular formula. It's also known exponentially decaying moving average, and I think there are 2 other names. Or you can use our libraries. We have a set of Go libraries in the Go libs GitHub repo, and one of those is called EWMA, Exponentially Weighted Moving Average, and you can just use our implementation. We are providing 2 different data structures here. One is the normal EWMA, which takes the absolute value. So it's much like the Linux load average. You take a value like 20 or 15 or something, and you put those values as often as you wish. But in order to get rates like packet rates, you need to actually do some inversion, some different maths. So for that we have EWMA rate, in which you just tell, okay, packet arrived, packet arrived, packet arrived, packet arrived, and the algorithm will tell you, oh, by the way, with this decay factor, with this half-life, this is the smoothed out average. So hopefully this was useful. Next time you will think about packets per second, you will know that you probably want to kind of smooth it out, and now you know how. Yep. That's it. Okay, so let's move on. Let's move on to the next exciting algorithm. So once again, our problem statement, we want to know how many packets per second are hitting each of our IP addresses. And in the naive implementation, again, we will have a table. Now we defined what we mean by PPS. We mean the EWMA. And what's the next problem? The next problem is that actually we have plenty of IP addresses. At CloudFlare, we actually do have plenty of IP addresses. So we probably could, but we don't want to afford to store a row for each IP address in memory. So we need to save the memory. We actually don't want to store millions and millions of rows that will have a value of 2 or 3. We don't really care about those kind of bottom values. We care only about the top headers here. So for that, we are encountering a top-end problem, also known as heavy hitters problem. This is a problem. This is again, streaming algorithm in which you put data into a black box, and the black box will magically tell you, oh, by the way, out of the items you put in here, I know that the top K ones, the top couple of ones, are those. And the algorithm is approximate, so it has some error bounds, but it has fixed memory, so it will never blow up memory. You can define, I don't want it to use more than X kilobytes of memory, and you have some guarantees based on that. It's very useful. It's very useful for other things like top URLs, if you want to see in real time what URLs are your customers hitting, or what are the top IP addresses that your customers are using, or any other real-time metric you want to see at top hitters. This is the algorithm you can use. The top-end problem is quite a general problem. There's also another, there's one of the algorithms called count min sketch, which I'm not an expert on, but the one I will describe is called space saving. Now, I know that describing algorithms requires some brain power, but please do bear with me, because I think this is actually quite simple. And hopefully in 5 slides, which are hopefully very simple, you will know how to implement space saving yourself. So if you have any source of data that you could use that for you, hopefully you should be able to use that. Okay, so space saving. So once again, bear with me, just a couple of slides, then I'll be hopefully easier. Okay, so space saving has in which you create a table with a fixed number of rows. It can be 30, it can be 100, whatever you choose. And it has 3 columns. The key one is the simple one, is that you put the URL there, or an IP address, or username, whatever you want. You put the thing that you count there. And then you have 2 columns, one is called count, one is called error. Let me describe how it works. So let's say we have a new event coming in, and let's say the key is Alice. So what we do is we find an empty row. Okay, we found one. We put Alice in the key column, and we increase the counter by 1, because this was one event. So the generic space saving counts number of events, counts how many times something happened. Okay, let's go next event. Let's go that Alice happens again. So we just bump the counter because we found it already. Let's say that Ben was the 3rd event. Okay, so we find an empty row and we bump up the Ben, so large and simple, and finally Charlie, and now we have full table. Now it gets interesting. Okay, so what happens if the new event comes in right now and it's not Alice, Ben, or Charlie? Let's say it was Eric, whoever Eric is. So how the algorithm works is you find a row which has the lowest count value, and then you choose this row and you overwrite the Ben. You basically throw out Ben. And you overwrite with the new key, which is Eric, and now is the only magical bit in this algorithm, which is you move the count column to the error column. Actually, you add the value from the count column to the error column. Okay, so there is this arrow with a plus there, and then finally you bump the count column because Eric happens once. That's it. That's how the algorithm works. You're done. You don't have to think about it for now. Okay. So what properties does it give you? Well, when you report of how many times an event happened, the algorithm gives you bounds. If the error is 0, there are no bounds. We know exactly that Alice happened exactly twice. So the error guarantees are very strong. The same for Charlie, we know exactly. But for Eric, we kind of are not really certain what happened. What we do know is that the count column is 1, so we are absolutely 100% certain Eric happened at least once. We counted that. We know it happened once. But there is something else that we moved to the error column, which could have been something different. It could have been Eric, kind of. In this case it couldn't, but in general speaking it could have been Eric, or it could have been something different. So the algorithm will report in this case that Eric happened at least once, at most twice. That's it. So basically the algorithm gives you some error bounds of how many times an event happens, and it also gives you guarantees that if any of the events will happen more than 1/n, in this case we have 3 rows, so if any of the events happened more than 1/3 of times, it will be seen here. So if you create a table of size 10, you will know that if there is something happening more than 10% time, it will show up. If you create a table of size 100, if something happens more than 1% of all of the events, you will see it there. So it's pretty cool. Okay, so again, you can play with that. I told you it's very simple, or you can use our implementation again in the GoLibs package. What about rates? Here we described counters, absolute values, how many times Alice happened, how many times Ben happened, or something like that. It's not really applicable to the packets. I don't really care about how many packets I received this IP address. Like, it will be a big number. I don't care. I care about how many packets per second. So tweaking this algorithm to actually do rates, like packets per second, is a bit tough. So this I don't recommend you implement at home, and the guarantees are a bit changed, and so on and so forth. Anyway, you can use our implementation again. So yes, so now you know how to do that, to use that, hopefully. All right, so yes, so hopefully, again, this could be useful. All right, so now our custom algorithm. So the problem we were having so far is that we actually don't care about IP addresses. We care about attacks. How we define attack? That's a bit tough. But what we do know is that when we see many events happening with a very similar pattern, like here, let's say that we have many attacks to many IP addresses, and let's say they are all within one network subnet, then we really don't want to have reported like 200 attacks. That's not very efficient. Instead, we want to have what is shown at the bottom. We want the system to say, oh, by the way, I don't know about the detailed attacks, but I know that this subnet is being attacked. This is kind of stronger signal in this case. So this kind of we want to aggregate the signals when we need that. And unfortunately, this is kind of quite a complex problem. There is a well-known implementation, a well-known definition of the problem. It's often known as hierarchical heavy hitters, when we basically want to aggregate those kind of signals and pull up the most specific ones hand-wavy. But it's actually quite hard to implement. So instead, we kind of simplified this a bit. And what we did is we have an algorithm that basically has a kind of hard-coded path for this hierarchy. It's not a hierarchy anymore, by the way. But that way, it's simple to implement, and yeah, and it kind of works for us. So how it works is in a very similar way. We have those tables. We create different tables for each aggregation layer. So the middle table is what I described before, which is packets per second per IP address. The table on the right is packets per second per subnet, and the table on the left is more specific one, is packets per second per port, or something like that. But the point is we have many tables for different aggregation layers. So for example, when we think about that, if you don't really care about, if you want to be more generic than say, I want to find top N URLs hit in my website, you may want to be more specific. You may want to say, oh, by the way, if the referrer is fixed, I want to see that as well. So now we have two dimensions, right? You have URL and referrer. Or you can add third dimension saying, oh, by the way, if the IP address is fixed, then I want to see all those three things. So this is how you kind of build that up. You create the very specific table with all the three parameters, and less specific table, and less specific table, and less specific table. So basically, you can define your own aggregation layers. Okay, so for sake of simplicity and kind of description, let's say we have a new sample coming in, and we bump the counters in each of the tables, and let's say this, for simplicity, let's say that's it, and then we report once a second or once in a while what are the top events, what are the top things, and let's say that we just say that we report all the items visible here above some threshold, and the threshold is like say 1 million packets or something like that. In this case, the algorithm will print report like that, which will print all the aggregations layers. That's not very interesting. It's actually not very useful. It's like, yeah, I see those stuff. There are plenty of packets coming in, but I don't really know much. But let's fix the algorithm. So let's do it like that. When a new sample comes in, we iterate over all the tables, but we do it in an order from the most specific to the less specific, and we also look at the counter. And when we see the table that has counter above threshold of 1 million, we stop there. We do not go to the less specific table. So basically, in this case, we see we are bumping the counter in the most specific table of the IP and port, and we see this particular row has value of more than 1 million, so we don't increase the counters in the less specific tables. And this guarantees us that the less specific tables will not see the counters coming up. So now when you print the report, it will actually show you the most specific attack or pattern as here. If you think about the details of this algorithm, it's not perfect, so I don't recommend billing based on that, because it actually has quite significant errors if you look at the details. But the point is, it works. It's fairly simple to implement. It's fairly nice complexity, CPU complexity as well, so it's fairly easy. And it scales well. So we actually are using that to detect attacks and to try to have as specific attack description as possible. So we are adding more dimensions kind of every day as we are figuring out what patterns are the attackers actually using. So anyway, it works. So yep, it worked for the practice. The error bounds are not perfect. It's just because you bump many counters, so that's why it doesn't give you proper counters. Anyway, okay. Finally, my favorite algorithm. which we started using only recently. And we are using that for a bit different use case. So what we have here is an example of one of our kind of dashboards in which I can see the number of packets per second hitting particular target IP address, our IP address. And then I see also what data center this IP address is being hidden. And then the last column is the most interesting, which is, okay, the algorithm estimated that there is about 57,000 subnets being used for this attack, IP addresses. Okay, so we are basically, in this case, we are trying to approximate how many unique IP addresses we see here. For that, we will use a hyperloglog algorithm. We are using at CloudFlare this algorithm for many other use cases. It's also used for reporting, so if you log to our CloudFlare panel, you should see some statistics which are derived from hyperloglog in totally different system. But this is a very interesting algorithm. So it's used for estimation of cardinality, of how many, it doesn't tell you what are the top n items, it will tell you how many of them there are. So how it works is basically a black box, again, to which you feed this infinite data stream with Alice's, Bob's, IP addresses, whatever you want. And the hyperloglog can tell you exactly one thing of the output. I have no idea how many events you put in. I have no idea what they were. I don't know anything. Maybe it was one event happening a million times and other two happening once. I don't know. But I know there were n number of unique things you put inside. So it's basically a box that tells you how many unique things you put inside. It's kind of a set thing. And that's it. And it also has a fixed memory cost, so it's pretty lightweight. And it's very, very, very useful. It may not strike you as a very useful algorithm at first sight, but I'll explain that. It's because it has one other interesting property, which is you can do union of two hyperloglogs. So you can take two of those black boxes, and you can join them together, and they can answer you what is the number of unique items kind of summed up, right? And this is very interesting, because with that you can actually have multiple, the hierarchy of hyperloglogs, and you can get different aggregation, different things. Okay, so again, you don't need to write the implementation, although yeah, I think actually the maths here is pretty hard. Anyway, we didn't write the maths ourselves, so this is some GitHub repo, some public implementation. The API is very simple. It's like you create a thing, you give it one parameter called precision, and you add items to it, and you can take count. So it's trivial to use. The precision is basically how much memory it should use, and it's a number of bits. The normal recommended values are between 12 and 16. So 12 bits is 4,000 kind of registers in the data structure. Anyway, very exciting data structure. So what about rates? Again, it can give you only counters of how many unique things there were. Well, people are using that for kind of rates-like things, kind of moving up in time. And how they do that is they have a hyperloglog for each, let's say, hour or day, for each time period. And then when you ask a question, how many unique things did I see over last 10 hours? You basically take last 10 hyperloglogs, they can take a union of them, and then you know that I know that in last hour there was 1 million or whatever, 100 of unique IP addresses, URLs, whatever you want. But if you count over 10 hours, I know exactly how many of them because you take the union out of the last 10-hour hyperloglogos. So you can get pretty decent approximation here. And there is a side note here, which is I couldn't find the link here, but I seen a presentation some time ago about some hard drive vendor that are actually putting hyperloglogs on their firmware and their hard drives in order to figure out what's the access pattern to the disk. And this is obvious for the hard drive vendors, but it wasn't obvious for me that apparently people are not using their disks at all. So even though you have 300 gigs on the hard drive or even more, it's actually every hour you're using, I don't know, last 1 gig, so, or whatever, very small amount. So what they did is they had hyperloglogs for a day, for a week, for an hour, and basically with that they were able to approximate based on the sectors you access that, okay, in last hour there were, I don't know how much data you transferred, I don't know how many times you hit those things, but I know you hit at most, I don't know, 1 gigabyte of data, and so forth. So yes, hyperloglogs are very useful. That's all I have. Hopefully I inspired you to play with streaming algorithms. We are using them for real-time data for our DDoS mitigation systems. We are using that for, especially the hyperloglog, for other systems as well. But the point is they are awesome. People generally, I think people are not educated enough. People don't understand how streaming algorithms works. I think they are brilliant. And they are applicable in so many different use cases, from top URLs in your website to many other real-timey thingies. That's hand waving. Thank you.